Welcome back to this course of chemical crystallography. I am again going to start from the last slide where we stopped in the previous lecture, and I gave you one assignment to do. So here we have a plane marked as blue and it has intercepts only along z axis. So what we should do in this case? See, what has happened is, when the line that we have drawn from the topmost point to this point, this is the line that is traveling along x. It has traveled one unit cell along x and it has come down from top by 1/5 unit while traveling 1 unit along x. So, if it travels 5 such units on this side, then this will go and meet the x axis. So, the x intercept will be 5. Now, on the side of y, this has traveled 1 unit along y, but it has come down by 5/6 along y. So, if it has come down 5/6 along z while traveling 1 unit along y, at 1 along z will be traveled, 1 along z will be traveled in 6/5 unit along y. So, the y intercept will be 6/5, and from this point the intercept on z is 1. So, these are the actual intercepts. So, the reciprocals will be 1/5, 5/6 and 1. The nuclear fraction, so multiply by 30. So, here you get 6, 25, 30. So, the Miller indices for that particular plane becomes 6, 25, 30. This is to introduce that the Miller indices can be large as we are writing, like 35, 25 and so on. Depending on how high the resolution data is, you can slice the unit cells into smaller and smaller and smaller fractions, and that is where we end up getting Miller indices for different planes which are reasonably high. So, I would like you to practice these Miller indices for next few days. So, we would like now to highlight some of the general principles. As we have already seen that if a Miller index is 0, the plane is parallel to that axis. The smaller the Miller index, the more nearly parallel the plane is to that particular axis. The larger the Miller index, the more nearly perpendicular a plane is to that particular axis. Multiplying or dividing a Miller index by a constant has no effect on the orientation of the plane, but it indicates a parallel plane. Miller indices are almost always small for routine data because we are only looking at a very small fraction of the 2 theta angle at which we collect the data. So for your homework, which I would like you to try to draw different planes like 1 0 0, 2 0 0, 1 2 bar 1, 1 2 1, 1 1 1 bar kind of planes, and practice drawing these different planes within the lattice, within the unit cell. Some important aspects of the Miller indices for planes continues. The planes and their negatives indicate the same plane viewed from opposite side or different. This is different for directions. So if you have a plane HKL and you are talking about H bar, K bar, L bar, you are looking at the same plane from two different directions. Whereas in case of crystallographic directions, a plane HKL is opposite in direction compared to a direction H bar, K bar, L bar. So they are two opposite directions. Planes and their multiples are not identical. Again, this is opposite from that of directions, which means the plane 1 0 0 and 2 0 0 are not same, but in case of direction, the direction 1 0 0 and 2 0 0 indicate the same direction. In each unit cell, planes of a form HKL represent groups of equivalent planes that have their particular indices because of the orientation of the coordinates. These groups of similar planes are represented with the curly brackets. So these are called as family of planes, as we have already indicated. So these planes are highlighted as a family of equivalent planes 1, 2, 3. In cubic systems, the direction that has the same indices as a plane is perpendicular to that particular plane. Due to the symmetry of the crystal structure, the spacing and arrangement of the atoms may be same in several planes. These are known as equivalent planes, and the group of equivalent planes are known as family of planes. So to conclude this section, I am bringing this slide in that when we try to write the Miller indices, when we write it using the first bracket like HKL and we do not have any comma, it indicates a crystallographic plane. When we write HKL within the second bracket as indicated here, we are talking about equivalent planes. When we are indicating the HKL within the third bracket or the square bracket, it indicates a crystal direction. And when we represent HKL within this greater than less than sign, they are called the equivalent directions. So with this we will conclude the part where we needed to know the Miller indices for different set of planes in different crystallographic systems. So now we would like you to concentrate on a different topic where we would like to see what are repeat distances and linear density. A repeat distance means the distance between the two adjacent lattice points in the unit cell. So in case of a face-centered lattice, what we have is an atom at the center of the face and an atom at the. In the figure here, what we see is that you have one atom at the center of one atom at the corner of the unit cell, one atom at the center of the face. So the face diagonal, which is a distance called root 2a, the repeat distance is half of that. So by moving along half of this diagonal, we reach one particular lattice point. So for simple cubic, the repeat distance is same as A0. For face centered lattice, it is half of the face diagonal, that is A0 by root 2. And in case of body centered lattice, the repeat distance is half of the body diagonal, which means half of root 3 by A0, that is root 3 by A0 by 2. So the linear density is the number of lattice points per unit length along a crystallographic direction. So linear density is basically the number of repeat distance per unit length of the direction vector. So for FCC copper, when the edge length is 0.36151 nanometer, the repeat distance is the face diagonal. So we calculate it to be 0.256 nanometer. So the linear density is 2 repeat distances divided by the half of the body divided by the body diagonal. So 3.91 lattice points per nanometer. And linear density is the reciprocal of repeat distance. So similarly, we can define another term called planar density, which means area of atom centered on a plane divided by the area of the plane. Because not all the planes will hold atoms, or not all the planes will hold the center of the atoms, and then the planar density of those planes will be different from the ones where you have large number of atoms. So in case of simple cubic lattice, which means it is a primitive lattice, and in that case what we have is that the 8 corners are occupied by 8 atoms or 8 lattice points, and those 8 lattice points are such that the radius r is such that it touches the two surfaces, which means if I just draw one particular plane of the face, it should look like this. This is the radius of the atom r. That means 2r equal to A0. Now for this particular face, the area is A0 square, and we have 1/4 contribution from 4 atoms. That means we have contribution from 1 atom, and the area of that atom covered on that plane is the following: area covered by the atoms is nothing but pi r square, because it is equivalent to 1 atom, because you have 1/4, 1/4, 1/4, 1/4. And we know r equal to A0 by 2. So here we write pi A0 by 2 square, that means half pi A0 square. So the planar density for this 1, 0, 0 set of planes, which are the faces, would be the area covered by the atoms, half pi A0 square divided by A0 square. So this is nothing but equal to half pi. So now if I want you to determine the planar density the 1, 1, 0 plane. How should we do that? We first should draw the 1, 1, 0 plane with the atoms placed on that. Along this edge, which is A, these two atoms are going to touch each other. So we write it like this. But along the face diagonal they don't touch, so there is a gap. Now, what is the length of the face diagonal? The length of the face diagonal is root 2a, or rather root 2a0. So what is the area of this face? Area of 1, 1, 0 set of plane is root 2 a0 square. Area occupied by the atoms is equal to, once again, pi r square, which is equal to pi a0 by 2 square, that is one mistake here we have done is that this 2 should be here 4. So 1/4 comes here. So now we do the same thing here as well. So 1/4 pi a0 square. So the corresponding planar density will be 1/4 pi a0 square divided by root 2 a0 square, which means pi by 4 root 2. So now we see that the planar density of 1, 0, 0 plane and 1, 1, 0 plane are different. What will be the planar density of this particular plane? What are the Miller indices for this plane? The Miller indices for that plane is 0 to 0. You see here in this plane we don't have any atom centers located. That means no atom has contribution on this plane if we consider hard sphere. So the planar density is going to be 0. Now let us try to work out the planar density of body-centered cubic lattice, and we will try to see how the planar density changes for different planes like 1, 0, 0, 1, 1, 0 and 1, 1, 1 planes. So let us first draw the body-centered lattice. As you know, the body-centered lattice has 8 lattice points at 8 corners and a lattice point at half, half, half. So we have atoms at 8 corners and at the center of the lattice. So in case of body-centered lattice, the close pack direction is the 1, 1, 1 direction, that is the body diagonal. So if the edge length is A or A0, the body diagonal is root 3 A0, and it is close packed along the body diagonal. So when we connect corner to corner, we pass through two atoms. So the diameter of two atoms is incorporated here. So the length in terms of atomic radius is 4r, which means r equal to root 3 by 4 A0. So now with this in mind, let us start working out the 1, 0, 0 plane. The 1, 0, 0 plane is the face, one of those 6 faces of a cube, and remember, since the body diagonal is the close packed direction, the atoms do not touch along the face. The edge length for the face is A0. So the area of each face is A0 square, and the area covered by the atoms is nothing but pi r square, because 1/4, 1/4, 1/4 and 1/4 gives you pi r square, which is equal to pi r square is root 3 A0 by 4 whole square, which is equal to 3 A0 square by 16 pi. So now the corresponding planar density turns out to be 3 by 16 pi A0 square divided by A0 square, which is equal to 3 by 16 pi, which is equal to 0.59. Now if we do it for the other plane, which I told is the 1, 1, 0 plane, the 1, 1, 0 plane is the plane which I am drawing in red. So in this plane, we have a body diagonal connecting the other corners. So if we try to draw the 1, 1, 0 plane in case of body centered cubic lattice, we would have 4 atoms at 4 corners, and the central atom would touch the 4 corner atoms along the body. So the edge, one of the edge is A0, which is this one, but the other edge is the face diagonal, which is root 2 A0. So the area that it encompasses is root 2 A0 square. Now inside this area you have 4 1/4 portions of the atom and 1 full atom. That means total 2 atomic area is covered in this 1, 1, 0 plane of body centered lattice. So covered area is nothing but 2 pi r square. So this 2 pi r square can be written as 2 pi 3 A0 square by 16, which means it is equal to 3 by 8 A0 square pi. Therefore, the planar density would be 3 by 8 pi A0 square divided by root 2 A0 square. So this value would turn out to be 3 by 8 root 2 pi, which is equal to 0.89. So now let us see what happens if we try to do the same for the plane 111. Now you see that interestingly this 111 plane does not contain that point which is at half of half. So the 111 plane, which is a triangular plane, should look like this, where we have three corners occupied by the atoms and the every side is corresponding to root 2a. So the area under this triangle is nothing but root 2a square root 3 by 4, which means it is equal to root 3 by 2 a0 square. Now the area covered is equal to 1/6, 1/6, 1/6. That means 3 parts of 1/6 means half pi r square. What is r? R is equal to root 3 by 4 a0. So a square is 3 by 16 a0 square. That means the planar density is equal to 3 by 32 pi a0 square divided by root 3 by 2 a0 square. So you can work it out. So it is equal to root 3 by 16 pi, which means that the value turns out to be 0.34, a very small number. So this indicates that in case of body-centered lattice, the plane 110 has much higher planar density compared to that of the 111 plane, and the face, the plane which corresponds to the face, which is 100 plane, has an intermediate density. So in this lecture we have learned how to calculate the linear density and planar density of different systems. So what I would like you to do yourself is to calculate the planar density of face-centered cubic lattice for the planes 100, 110 and 111 and compare their values yourself. So today we have seen how to identify the HKLs for crystallographic planes, and we have learnt about the linear density and planar density. Then in the next class we will continue in this direction and we will see how these planar densities can be utilized to identify the strength of those diffractions from different crystallographic planes.